Welcome. In this video, I wanted to give you a bit of a application or think of it as an aid on how to calculate work done. And this should help you approach any kind of problem. So if we are given a task to calculate work done by a given force, the first important question we need to ask, we need to determine first, is the force a constant force? That's the first important question before we do anything, before we calculate anything. No matter the details of the question, no matter how little the detail or how too much detail there is, first things first, we need to determine, is the force constant or not? If the force is constant, then the way we calculate the work for a constant force is given by this. Notice here, there are two ways of calculating work done by a constant force, and these two ways are equivalent. These two ways are equivalent to one another. Whether you use one way over another depends on how the data is supplied to you. Typically, you would use this approach, that is of finding the dot product directly, if the information was given to you in unit vector notation. That is, if your force was given to you in unit vector notation, and the displacement vector is also given to you in unit vector notation. So this is the approach we would use. This is the approach we would use for a constant force, which is given to us in unit vector notation, and the displacement is also in unit vector notation. However, that's not the only way that the information could be supplied to us. Sometimes the question might give us the magnitude of the force and the magnitude of the displacement, and some information which enables us to determine the angle between these two vectors. So beta is the angle between the force vector and the displacement vector when they are attached tail to tail. So this is critical. If we find out that our force is constant, is indeed constant, then we have this available to us, these two equivalent methods. Now, what happens if we inquire about the force and we find that the force is not constant? Well, the way you calculate work done by a non-constant force, or sometimes we call it a variable force, the way you calculate work done by a variable force is to take the integral. It is to perform the integral of that force over that displacement vector, over the displacement, whatever displacement is applied to us. So I do have a video that reviews the algorithm of polynomial integration. I believe if you need clarity on that, you're welcome to watch that video, but right now we'll just refer to it as just I'll assume that you know how to integrate. Okay, so let's apply this flow chart in two examples. Okay, so for now, don't pay attention to the red lettering, but let's consider the question itself. In this question, we're given a machine which carries a 4 kilogram package from some initial position given by that. So this should be a key to you. This should already get you thinking that, okay, well, our position is given in unit vector notation. So the object, the package begins at this position and it ends up in this final position. This means we can calculate the change in position or the displacement vector. So we could take df, d final minus d initial, that will give us the change in position or displacement. And we're told further on down the line, it says the constant force applied by the machine on the package is given by this. Notice here that they do supply us with these two words which are greatly helpful to us, but even if these words were not supplied, we could inquire about the force just by observing it. Look at the components. The first component is 2.0. Now, 2.0 newtons does not depend on anything. It's not a varying thing. 2 will always be 2. It doesn't change, it will always be 2. And on the J component, or the Y component, the force is 4 newtons. Again, another constant. 4 will always be 4. And finally, in the Z direction, or the K hat component, we find that this is 6.0. And again, 6 is just a constant number. So this suggests to us that this force is a constant force, even if these words were not included. Because this force is constant, if we're going to calculate the work done by this force, according to our flow chart, we have this luxury that we could use either this method or this method. Now, we need to consider, based on the data, the way the information is supplied to us, it probably is clear that we will not be able to use this approach. Of course, we can always calculate the magnitude of the force. That's very easy. We would square the components and add them up and take the square root of them. And the same with the displacement vector. We would take the difference of this and we would calculate its magnitude. So these two things can be computed. But what about beta? That is, what is the angle between this force and the displacement vector? To find beta will be a very difficult task. And this task is even more difficult because this problem is three-dimensional. So we cannot even plot the situation to help us figure out what beta is. So this kind of a roadblock, this kind of a hiccup in our way, this is actually pointing us that we probably should be using this approach. Now, let's go ahead and use this approach. First, we need to find d bar, and d bar here will be the displacement. Unfortunately, here we use the same symbol for position and for displacement, but I think this should be clear that by finding the change in position, we obtain the displacement. And if we were to go through with it, we will find that our displacement vector will look like this. 7.0 meters in the I hat, 11.25 in the J hat, and 7.0 in the K hat. Now, if we were to calculate the work done by this force, as the object undergoes this displacement, then we can use the good old dot product. Remember, the dot product says we multiply the x with the x component, and the y component with the y component, and the z component with the z component, and no I hats and j hats should remain. That's the key about the dot product, is that it was a scalar product, and what it produced was a scalar, a number. This should be something that could help you figure out whether you've made a mistake or not. If you calculate work done and you find that there's a I hat or a j hat, this should be a big warning sign that you probably have made a mistake. Because remember, work done is a scalar quantity. So there shouldn't be any I hats or j hats. So this is just something you could test yourself as you solve problems. Okay, so this demonstrates how you calculate work done by a force which is constant, and this force is given to us in a vectorial form. Let's consider a different scenario. Let's consider this force. Here we're given a force which acts on a particle, and it does so such that the particle moves from position x equals to 0 to x is equals to 3. For now, I will discard all the other details about the problem, and also I will not particularly focus on what we're asked to find. But I just want to demonstrate how to calculate work done by this force. Okay, so our force here is given by c times x minus 3 x squared I hat. So, is this force constant or not? Remember, we're calculating work done. The first question we need to ask is the force in question, is it constant or not? Well, this force has x's on them, and x is a variable here. You see, x will begin from 0 and it will change to 3.0. Because x is something that changes and the force depends on that x, that means this force will also change. So this force is a varying force. Let's consider, what is this force when x is equals to 0? When x is equals to 0, this force, when we substitute x equal to 0 in the formula of this force, actually this should be like that. That's a mistake on my side. So when we calculate the force when the particle is located at x is equals to 0, notice this suggests to us that the force is also 0. But what about when x is equals to 1 meters? We substitute 1 for every time we see x. Notice what we obtain. We obtain that the force is no longer 0, but it's c minus 3. This is testimony, this is testimony that the force is not constant. When x is equals to 0, it was 0, but now x is equals to 1, it has also changed. Now, how do you calculate work done by a force that's constant? Now that we've established that, now that we have established that our force is not constant, how do you calculate work done by a non-constant force? Well, the way you do that is by performing the integral. And if you were to perform the integral, you will obtain something like this. And when we substitute the values, we would find that the work done by a varying force in this context is going to be given by 9c over 2 minus 27. And this should be in joules. This findings here, these findings should be in joules. I hope that gives you a bit of an idea on how to navigate problems. There's no need to panic. You just need to be comfortable with your instruments. Before you begin a problem, always ask yourself, is the force I'm required to find, whose work I'm required to find, is it constant or not? If yes, then we know we will be applying this left side of the flow chart. However, if our force is not constant, then we simply would use this side. So I will conclude the video here. We will continue in the next one to talk about the connection between work done and energy. But for now, I'll stop here and see you in the next one.